Okay, so we have defined the pt to be f of x plus p plus f of x minus p over 2. So p in the small interval. Relate s of x equal to g 0 plus. 0 plus actually is the limit of p goes to 0 plus. Means that it goes to 0 from the right hand side. And 2. Okay? If whenever the limit exists. So whenever the limit exists, because this function is defined for every x, right? Maybe I will say for a given, maybe this is better. So for a given x, we define a function, and with that, if the right limit of the g at 0 exists, then we define this quantity as s of x. And we know that if f of x, if the function f is continuous at x, so suppose if f is continuous at x, then we know that the limit equals to 0 plus. By the continuity, when this value approach to f of x from the right hand side, right? Because continuity, so we have f of x plus f of x divided by 2. Okay? This is by continuity. And so the value is equal to f of x, and which is just s of x. So if f is continuous at x, then the limit exists. Okay? And the s of f is equal to f of x. So they are the same. Now we will give a condition that this is true, because we want to apply Finity theorem. So we have to make sure that that this ratio, this function of p, is integrable. It's absolutely integrable over this small interval. So we take a remark here. Right? So if the periodic function f has the left-hand limit called f of x minus, and the right-hand limit f of x plus. At a point x in R, then we know s of x, which is equal to, defined by this one, is equal to the average of the left-hand limit and the right-hand limit. Okay? So this one exists for x. Yeah, so we know. So if the periodic function has the left-hand limit and the right-hand limit at the point x, then s of x exists and is equal to the average of the left-hand limit and the right-hand limit at the point x. Okay, so that's fine. Okay, so this answer the first part here, G, this quantity exists. So if we know the periodic function has the left hand limit and the right hand limit, then this is true. Okay? And we know what is that? This is just the average of the left hand limit and the right hand limit of x. What condition, what convenient condition to guarantee here, guarantee the statement here? Well, so furthermore, if f has the left hand derivative and the right hand derivative at point x, i.e., so what do we mean? Left hand derivative, right hand derivative, right? Maybe you are not familiar with this. The two limit. Okay? We take the derivative from the left hand side. Right? So, from the left hand side. So, and the t goes to 0 plus. Okay? So, t always positive. Okay? And so we approach x from the left hand side of x. Right? So, this is the function value minus the left hand limit, because we assume the periodic function has left hand limit as well as the right hand limit. So we divide. And the difference is minus t minus 0, right? So we have to divide by minus t. Now this limit exists. We call f. And so this one is the left hand derivative. Okay? This is the definition of left hand derivative. How about the right hand derivative? Well, we approach x from the right hand side, so we add t minus the right hand limit of f of x, and t minus 0 is t. This is called the right hand limit. Alright, so the meaning, so to say that f has the left hand limit, left hand derivative, and the right hand derivative, if these two limits exist. Is that okay for you? So this is the basic definition. Alright. Then now we interpret these two limits by using the epsilon delta. Alright, so then for all epsilon, there exists a delta such that for this one is that x minus t minus f of x minus divided by minus t minus l is less than epsilon. And fx plus t minus x plus t minus r is epsilon, right? For all 0 for dou t in between 0 and delta. Okay? This is just the interpretation, right, by using epsilon delta language. Now, in particular, I choose, right, in particular, there is a positive less than pi. So I choose delta small enough, right? Such that f x minus t minus fx minus this one less than 0 plus epsilon. So that we can, the epsilon can be selected so that the delta is quite small, right? Quite small. And this one implies this one, right? This one implies this one. By triangular inequality of the absolute value. Why? Well, we know, maybe I'll do it for you again. This is this one can be, I think this technique has been used, right? You mass L plus L, right? And by the triangular inequality of the absolute value, so this is minus T minus L. Right? This is triangular inequality. And this one is already present, so this is L. Okay, so we have that. And then similarly, so, and right, that's upper bounded by this quantity. So this ratio is upper bounded by this quantity, and this ratio is upper bounded by this quantity. For all t in here, okay, for some. Now, since gt minus g0 down, g0 plus divided by t, okay, can be rewritten here. I rewrite this one here, x minus t plus t divided by t minus t okay, I can write it this way. Why? Because we know this one is equal to right, we have that. Okay, and we know this one is equal to right. So the difference, when you take difference, this is become to this one. Is that okay? Right? When you have that, then I check the absolute value. And again, by triangular inequality, this is less than equal to, because this one, L, divided by 2 plus epsilon. So this function has an upper bound. If a function has an upper bound for all t in this interval, it is of course absolutely integrable over the interval, because its value has an upper bound. Okay, so this implies that divided by t is absolutely integrable over 0 to delta. Okay, so now we can apply Dini's theorem, right? So if the periodic function has a left-hand limit and a right-hand limit, then we know that G0 plus exists. And furthermore, if f has the left-hand derivative and the right-hand derivative at point x, right, then this function is absolutely integrable. Right? So the condition required infinite theorem, is true. And so that we have the final result. But before that, let me consider a practical situation. A function f defined a finite closed interval AB is called piecewise continuous. If there exists a finite number of points A such that f is continuous on xi minus 1 to xi for all I when 1 and n, and the left hand and the right hand limit x0 plus fx1 minus fx1 plus fxn minus 1 minus fxn minus 1 plus fxn minus, okay, exists. Let me draw an example of piecewise linear function. So it's A and B here. Okay. And so we have all right. So that piecewise, because we can find points. So here we have x1, x2, x4, x5, x0. So in each open interval, the function is continuous. You see, they are continuous. Right? But at the point, they have left hand as well as right hand limits. So you can see they have here the right hand limit is equal to this value. And it doesn't matter what is the value at this point. So you may say here, you may say here, okay, here, here, here. So the function defined at the point here is 0 up to x5 at the arbitrary point. That's fine. Yeah, that's fine. Okay? So this is a typical example of a piecewise linear function. Piecewise continuous, I'm sorry. Piecewise continuous function. Okay, so this is a piecewise continuous function. Okay, so for a piecewise continuous function, that it has right-hand limit as well as left-hand limit at every point. Okay, at every point. All right, so the theorem representation by trigonometric Fourier series. Right, so now we are able to answer our question. Right, so let f be a periodic function, okay, with period to pi. And this function is piecewise continuous. Okay? On the real one, I think that's fine. Furthermore, assume that f has the left hand and the right hand derivative. Okay? At each point. On the real line. Then the trigonometric Fourier series. Alright, so the trigonometric Fourier series generated by f. Okay, converge so converges to f of x except at point x where f is discontinuous. Right? So if f is piecewise linear, piecewise continuous like this one, and if f has the left hand and right hand derivative, actually you can see that for this example, it has right hand as well as left hand derivative. Okay? Every point. Then the trigonometric Fourier series generated by f converge to f of x when if f is continuous at x. And if f of x is not continuous at x, then the sum, right, of the series is the average of the left hand and the right hand limit of f of x. Okay. So this is the final theorem. we have. Okay, so in the future, if we are given a periodic function f with period 2 pi, and we know it is piecewise continuous, and we know that the left-hand derivative as well as the right-hand derivative of f exists at every point, then the trigonometric Fourier series generated by this periodic function f converge to f of x, to the function value, if f is continuous at x. For example, for our point here, the Fourier series converge to the function value f of x. And if f of x, f is discontinuous at x, then the series will converge to the average of the right hand and left hand limit. Okay, so the example is that so we have considered a periodic rectangular wave. Okay. Right, so it's okay, so we construct and we have generated a trigonometric Fourier series. So we know that this is equal to so this is the Fourier series, okay, generated by this rectangular wave. Okay. So now, by this representation theorem, okay, we can conclude that we have that the f of x is equal to the sum. So actually, this Fourier series converge, okay, converge. Right, so this is actually converge to f of x for all x in R except n pi. Right, so except n pi, that this, if except x equal to n pi, that this Fourier series converge to f of x. Okay. And the series, right, it's obviously equal to what? To 0 when x equal to n pi. Since the n pi, okay, since the right hand side for n pi, the right limiter is equal to 1, and the left limiter from here equal to -1. Is that correct? Yeah. 2k. If it's even, but if R is minus 1, we go to plus 1. No matter which one, when they add together, they become to 0, right? So the average is 0. All right. So we have the Fourier series representation, and you know that such functions satisfying all these properties, right, form a very broad set of functions in practice. So actually, I think in practice, all the periodic functions you observe belongs to this class. So this theorem is very satisfactory. Any questions? All right. So I have given you a more or less complete theory of the Fourier series representation. Okay, because that I showed to you that what is the necessary and sufficient condition for a trigonometric Fourier series to converge for a given point x. That is that we have the Riemann localization theorem. Okay. And the final representation theorem actually is very useful in practice. So basically, we have a very good answer to our problems. And that will guide our tour toward to the Fourier integral transformation later on. Okay. So I hope that you fully understand the material. And within the course of discussion, I mentioned several useful big theorems for you to use in here or in other branches of mathematics as well as engineering. Okay. So do you have any questions about the first section? Okay. All right. So if no, I will continue to discuss the second section. But in the first section, we consider periodic function with period to pi, but actually there are periodic function with period which is not to pi, right? So we have to consider general. So we have, I think we have a title, I forgot, general periodic function. Okay, so now f a periodic function, right? A periodic function with period 2L, right? So I use 2L, not L. So for some reason later you will see that. So f itself is a periodic function with period 2L, and which is again is piecewise continuous, right? One period, and has the left hand and right hand derivatives. each point of. Okay, so basically the function f satisfies the conditions required in this representation there. Okay, but this time we'll just relax the function to have period equal to 2 times L instead of 2 times pi here. Okay. Now, by changing variable, okay, so we let x equal to p to 2L divided by 2 pi squared, right? So we let the original f, so maybe I let x, okay, it's here. So x, we just say x is equal to, so this is L divided by 3. Okay, so now f of x is equal to f by our transformation here. So f of x is equal to something g, maybe I use h, right? Here. Okay, by this transformation, then so that h is a periodic function, all right, with period 2 pi. Okay, so by substitution, because in here f of x is a periodic function with period 2 times L, but when we do the change of variable, okay, so when we let x equal to L divided by pi times v, then this becomes to a v function, okay, and so the h, the new function h, is a periodic function with period 2 pi, okay, so and so this h function satisfies must be periodic, piecewise continuous function, okay, must be, and has left hand and right hand derivatives too. Okay. So, alright, so that h is a periodic function period pi, right, and satisfy the condition in term 2. So that, all right, so that the f of x equal to h of v. Okay, so right. So this comes to a0 plus summation bn an cosine v plus bn sine v. Okay, so we have that. Okay, so we expand h of v, right, by using the trigonometric system here, and we can come back to variable x by the substitution, because in here, so v is equal to pi L of x, right? So now we have a0 and an cosine pi n pi x divided by L En sine n pi x by L here. So we have that. Right, and which is called the trigonometric Fourier series. Okay. So another way, write it. So maybe simplify f of x, okay, with Fourier coefficient A0 equal to 2 pi h of v dv. Okay? H of v dv. And this is 1 over 2 pi. But h of v dv is f of L pi v dv here. And by substitution, that this is equal to x, so we have 1 over 2L. Delta x equal to 3. So we can come back to here. Right? So A0 actually is 1 divided by a period, and we integrate f of x over 1 period. And similarly, An is equal to okay, and so this is L cosine n pi x L dx. This is An. And Bn. Okay, so we can obtain the coefficients directly from f of x without the transformation go to h of v. Not necessary, right? So we can go to there. Okay, now there are some special cases when f of x is even. Okay, when f of x is even function, means that f minus x is equal to f of x for all x in R. Okay. Then we have Bn. We consider Bn. Because f of x is even, sine is odd. So this is an odd function. Okay? When you integrate odd functions in a symmetric interval, this is equal to 0. Okay. So if f is even function, then the Fourier representation becomes to S0 plus okay, so that f of x becomes to have a simple representation. Of course, you have to know that when I write this equality sign, I mean that this is indeed equality sign if f of x is continuous at x. Okay, and if f of x is not continuous at x, then the right the series will converge to the average of the right limit and the left limit. Okay, this is our mutual understanding. Otherwise, this is indeed is not correct rigorously. Okay, so maybe for awareness, I have to say that okay, so this is a real equality sign for those x at which f is continuous. Okay. Because f is piecewise continuous, so almost everywhere, right? Because only some finite point that f is not continuous in a period. All right, and so this is true for almost everywhere, for almost all the points on the real. Okay, so I have to notice that. Sure. Okay, and I think I have to stop here. If this is an odd function, it means that alright, so if the periodic function f is odd function, then a is 0. Of course, 0, right? Because this is odd. And the an is also 0, because this one is odd. Okay. In this case, f is equal to summation from 1 to infinity bn sine. Right, so you have only sine differentiation. Okay. Right, so I have stop here. And so I will assign homework, recommended homework up to this point for you to do exercise at home. And the next Tuesday, we will have the first quiz examination based on the recommended exercise. That means I will maybe change a little bit the value or some form from the exercise, right? Change a little bit, okay, for you. So please just really exercise the problems during the weekend. All right, and you are welcome to to come here next Monday from I think 7 p.m. to 8:30 for the practice session, because our TA will demonstrate some of the solution of the recommended exercise. And this is a good opportunity for you to ask questions to TA, okay? So, the same place here, Monday night. Right, so thank you, and I'll see you next week.